Go ahead.
Hey everyone, sorry for the delay there. We're just getting set up on the screen here. Welcome to our Geo for Dev workshop. I'm very excited this is our second Geo for Dev workshop that we're holding. This is organized by the Center for Effective Global Action, a West Coast hub for development researchers. And it's organized with our Geo for Dev or Geospatial Analysis for Development Initiative. Our partners are New Lake Technology and 3IE. And I'm excited to announce Marco Gonzalez Navarro, who will be leading our first workshop today on using a subway data set and radiance calibrated nighttime lights to measure urban development. So I'll hand it off to Marco and he can get us started. Thank you. And as a quick announcement regarding questions, we're going to be prioritizing questions in the room. Marco may be able to answer some online questions as he goes, but we may not be able to answer all of your questions because we don't have a lot of capacity in the Zoom room for answering questions outside of what Marco can answer on the technical side. So be patient, and we may have time at the end to answer any kind of like backlog of questions. But without any further ado, Marco, take it away.
Thanks, Sam. All right, thank you all for being here. I hope this is useful. There's, I imagine, like a wide range of backgrounds here. So I hope this is useful. I'll tell you where it's, a little bit of what we did with, I'm gonna motivate this with the paper that we wrote, Matt Turner and I, that was published in 2018. But then the workshop is more about getting into the back end and how things were calculated and how you can do this on your own and hopefully inspire some of your own work. Basically, let me start out with the following. Tell you a little bit about the paper, so that gives us some background as to why what we're doing here, and then we're gonna do a couple of calculations, show you some of the capabilities of R to do some of the analysis we did for this paper. Okay, but feel free to interrupt me. I guess for you to start out, if you have R installed in RStudio, that should be more than enough for you to kind of follow what I'm doing here. And I'll give you all of the resources. Sam, do they have access to the drive, to the folder, so they can download that? They do. Okay, maybe you can email them the R document, and I'll give the links in the chat to the resources that I relied on for this presentation. Okay, so first, let me tell you a little bit about the. Okay, so I was going to show you, not that. I wanted to show you the, oops. That's fine. I'm going to just do the PDF. Okay, so full screen. Okay, so this is a workshop organized by Geo for Dev, as Sam mentioned. I'm part of the SIGA network, so happy to do this. And I wanted to say first, thanks to Sam and SIGA. They took a paper of mine and said, oh, this, use some of these tools that people are interested in getting to know better. Shall we do a tutorial? And apparently it was Natalie. That's right, Sam?
Yeah, Natalie Ayers is no longer at SIGA, but doing it for PhD at Harvard.
So she's pretty amazing, and so she took the paper and wrote a little tutorial about some of the operations that we did in that paper. And I wanted to walk you through, I did things a certain way, but then Natalie did it in R, and I found that super useful because R is, open source, so it's free. Whereas for this paper, we did it with non-open source software. So I was using Stata and ArcMap, ArcGIS. Both of those, you have to pay for them. but now there are these open access tools that are available, so you don't have to pay. And I think that really opens the door to people that don't have a budget for research, right? Like students or even so that I think makes things a lot more democratic. And hopefully today you learn, see what we did here, kind of see yourself being able to do the same stuff and going on and doing your own projects. So that's my objective. Okay, so I'm going to copy this and put it on the chat, the tutorial here, so that you guys can see the tutorial that I'm talking about that Natalie developed at SIGA. So I'll put this in the chat. Here we go, the chat. You can view the tutorial for this lecture here. And so that's the link. It's Geo for Dev Subways Learning Module. And then the other one that we'll be using, I'll refer to it later, but I guess now's a good time, is the one on the radiance calibrated night lights.
I can post that, Mark.
Okay, great. Thank you. So maybe give them both so that they can, have that. That's available on the website, at SIGA's website, and you guys can go through it on your own. Okay. So thank you, Sam. All right. So so basically, I'm going to be relying on this module. I cut out stuff and I want to add a little bit of background as to the paper, and then kind of walk you through what inspired us to write this paper and how we did it, etc. Okay, and this kind of a little bit, some of the steps that we undertook using geospatial data. So, I mean, the fact that you're here means that you're interested in these topics. So, as am I and other people, I really think it's transforming research. These new data sets. In many fields, economics is one of them. So I am interested in urban topics. And so for me, the availability of these new data sets and new tools is just amazing. It's really changed my research agenda. And I feel like it gave me an edge as these things were being developed. I was kind of starting out, so it gave me an advantage over the older generations. So the same will happen with you, because a lot of this is still changing quite a bit. I kind of see some of the stuff that's going on, and I'm totally foreign to it at this point. So this was, I want to thank Sam for pushing me to do this and learning about this open access, open source software. Okay, so the paper that this is based on is Subways and Urban Growth. It was published in 2018 in the Journal of Urban Economics. And as I was saying, it's joined with Matthew Turner, who's at Brown. And basically, we were both interested in learning a little bit about how subway systems affect cities. And basically, one basic intuition we had is that if you have a transportation system with lower unit cost of transportation, then the basic prediction of a monocentric city model is that the city should grow, right? If transportation is cheaper, then people can move back and forth to their work, and the city can allow for a bigger size. Or you can think of it as attracting more people to live in a city where transportation costs are low. So we said, oh, the typical thing we mentioned when we teach that model is, something like a subway would potentially allow you to pack a lot more people at peak times to the downtown. And so we said, why don't we look at whether subway systems allow cities to grow more, and if they and how they affect the urban structure. So we focused on two things. One is the absolute size of the city, and for that we used I'll go through the data set, but basically population data sets from the United Nations and the night lights data that we're going to be using here. Okay, so first we asked, do we see that cities with subways tend to become brighter in years after decades after they build their subway? And two, do they become more or less decentralized? The other, research on this is previous to ours was on highways, And so in the US, you have all of these interstate highway systems, you have the interstate highway system, but basically some cities have more interstate highways crossing them and others have less, some have none, but you can use, some random variation in the original plan and say, okay, look at this city, it had more interstate highways crossing, so it has a lot more highways. What happened to those cities compared to those that didn't have, about the same size and controlling for their stuff, that didn't get one of these interstate highway, allowing it for, these high capacity highways within the city. And what that research agenda discovered is with highways, you get a lot more decentralization. So the paper there is Nate Bouncenau's QJE on did highways cause suburbanization? And so he does find, and for us now looking at things through the night lights, it's obvious when you have a highway, it looks like a neuron, right? Like you get this extension of the lights further out. So that was that paper. But we're going to find something similar here with the subways, is that they tend to decentralize cities, although surprisingly we don't find the growth effects. Okay, so those are the two main results of the paper, and then we'll go through how we calculated, how we came to that conclusion. And as I said, in terms of data sources, it's very simple. So one is, well, it took a lot of work, and I should thank all of the undergrad research assistants that we had. We asked them to go through to the internet, and there are these specialized websites like urbanrail.net, where people, this is crowdsourced, but they basically, a lot of people love trains, and they just write down, today this station opened, and they update the map, and every city that has a subway is pretty well up to date. You have pictures of the stations, etc. So what we did is we got a list from those maps of the subway stations everywhere, and it also comes with opening dates. So we basically went, this is a pretty manual thing because there's Wikipedia was also used, historical archives in some cases, especially the very older ones like the London subway. When was it really opened? It was really not an electrical train at the beginning. It was coal powered. People just died in there. And so at some point it became like a modern electric train, and then we had to decide what the starting date of the subway is, for example. Basically, I'll show you a little bit about how we did that, but basically it was undergrads with a CSV file with an Excel sheet, going through these and listing the stations and then figuring out what was the exact opening date of each subway station worldwide. This data set is now publicly available. I'll show you where we put it up. It's about 8,000 stations in the world, and about 200 cities have a subway system today. Okay, but that was basically hand collected from resources online. The other data source was the night lights data from NASA. These are widely used today. We use a special version that I'll walk through a little bit. Basically the typical night lights that we tend to see, which are annual, that people that are higher frequency, are basically go from a value of 0 to 63 per pixel. And so what you observe is that this top code, that 63, is pretty frequent in large urban areas. So you just see a big blob of white light, but you can't distinguish, the downtown being brighter than the suburbs. It just looks all top coded at 63. So we found out that there was a very special version of the night lights every 5 years that has non-top coded. So they set the sensor to be less sensitive on certain passes through the earth. And so you don't detect any of the lights in the rural areas. So that's not good for if you want to detect activity in, like, let's say, Africa, rural areas. But it is great if you want to study large cities, which was our case. What happens when subways are built, and those are typically built in very large cities. So we use those come every 5 years, which is fine by us because we were asking a long-term question, which is how do cities grow more or less or the same if they build a subway system. So we weren't looking for like a 2-month, 3-month effect. We were looking at, decades time frame. And so those are available online. And then finally, so we have the subways data. The United Nations population data set. That, let me mention a little bit about that one. The United Nations city population data set is really nice. It is basically, they take the most disaggregated census data for all countries that have available data. Not all of them obviously have available data. And then they apply the best, a common definition to what an urban area is, okay? And then they track the population of that urban area using population census data going back in time, up to starting in 1960 and up to today. And they have even projections going forward to 2050 or so. But basically, if you have a census every 10 years, they'll look at what each large agglomeration of above 300,000 people has, what type of population growth has it seen, okay? So we use that one to tell us where the cities are. And then, so we have the cities, location data with their population. The night lights is kind of a second check. So the night lights allows us to see, okay, does the city grow in light, at night? That's a proxy for economic activity, for population, etc. So it's not our main outcome variable, but in the paper, the main outcome variable is the population of these agglomerations. Okay, any questions? Yeah.
Do you look at gradients grading down from the side by side?
Yes, yeah, yes, we do. So I'll explain that in a second here in the tutorial. Yeah.
I'm just curious about the definition. Is there a reason why BRT and most trams are excluded? Does it include buses?
Good question. So that's my last bullet point here. So we had to define what a subway is for this paper and an accompanying paper that came out this year. And basically what we used was the following. It has to be electric powered. It has to be urban rail. So that excludes things like Amtrak between Chicago and LA, right? So it has to be urban rail, electric powered, and isolated from interactions with automobile traffic and pedestrians. Okay, that's our definition. What that means is it excludes a bunch of things. So it excludes, as I said, long distance rail, commuter rail, typically would be excluded, either because it's not electric or because it's more interstate. So if you have a Sacramento to San Francisco, that would not be part of what we want. It does exclude bus rapid transit, which is a big, mode of transport in some developing country cities. And then most trams. So Europe uses a lot of these trams. These are at grade, and people walk around the tracks. They stop at the lights, and we didn't. That was more in our minds. That was closer to a bus, and so we didn't want to use that, to get at the effects of. We thought these were more, let's say, less transformative, right, than a heavy rail. We're thinking of something like the New York City rail, Paris, London, the BART, etc., that have high capacity. Think of it being electric. Think of the BART. It is electric. It is does not interact with traffic, so it's an exclusive right of way. That means it can move around people much more quickly, and it's to move people within the urban area. So that was a definition we used. So it excludes things. So for example, some marginal cases that are ambiguous, let's say, is the Muni in San Francisco. So there's a municipal train system. The part that's underground does count as a subway for us, but once it leaves the underground and it goes to at grade, like in the outer parts of the city, then that part we just ignored. So that was kind of the ambiguous cases. Okay. Any other question?
So like why not including BRT? I feel that.
Why did we eliminate BRT?
Yeah.
Well, we thought it was a different thing. It was more of a, it's super interesting, and we're currently writing a paper on BRTs, but so we basically had to draw the line somewhere and excluded BRTs because BRTs are not electric powered, for example, and they do interact with traffic, etc. So we just stayed with this high capacity definition. This stuff anyone can do. I don't know why people didn't do it before, but basically maybe there's a smarter way to do it, but I'm telling you the way we did it. So we went to Google Maps And once we had the list of we said, okay, in Moscow, there are these, from Urban Rail, you get the map, more or less a map of the subway system. You decide, okay, that does count. We know the name of the station, the date of opening, but we didn't have the geolocation. And so we used Google Maps for that. Basically, we located them with the images or either the map. Sometimes they are marked. Sometimes we had to go, with the eye, what looks like a train station, and figure out and then you right click and it says what is here, and you write the latitude and longitude basically. So that was our subways data set with 7,000, about 8,000 observations. And then once you have the latitude and longitude, you can use spatial software to do part of the analysis. So what we used was ArcMap, and Berkeley has a license. You can ask for it. It's a pain that you have to renew it every year. It's kind of every unit has, Berkeley has a license, and it's pretty costly. So individuals don't buy those. So you have to associate it to a university to get one of those. So that's kind of, it does create a challenge if you're not in one of these places that has a license. You're probably not going to buy it yourself. So there's new options. So a new option is QGIS. That's freely downloadable, and it does almost the same things as the ArcMap. It also uses Python in the background, so you can write code like a stata.do file where you can keep track of what you're loading data sets, calculating statistics, and exporting data sets. So QGIS I've been using that more and more. I haven't even renewed my license because it's just, you have to call someone. So, okay, but we did do this in ArcMap. All right, and what's nice and what I learned from Natalie and her tutorial is that we can do some of these operations in R, geospatial. Stata can also do a little bit of at least drawing maps from shapefiles and populating values. But I feel like it's kind of clunky. It's not the same as QGIS or something like that. So let's go with R. So these are the two. First, you download R if you don't have it on your laptop. That's free. And then you download RStudio, and RStudio is just an interface for R. Let me go to that. So, any questions here? So, do you all have RStudio in there? Okay, great. And then, let me go to RStudio. Well, yeah, let me go there first. I guess I'll use mine. And what's nice about RStudio is it creates these with R Markdown. You can create these kind of HTML that has a little bit of commentary and your R work, and you can execute it in RStudio. So basically, yes. So I assume that you have R in RStudio, and then you can see these commands are in that tutorial that Natalie developed. So this is just a stripped down version of that. So first you install the packages, and the ones we're going to be using are Tidyverse, SF, ggplot2, Terra, Remotes, Stargazer for the tables, and LFE. LFE is for regression, and then there's this the RSpatial geodata, and this is what we're going to be using, as I said, to draw some of the subways using R. Okay, to get some of the graphs from the paper. Okay, so we can download these libraries. Sorry, load these libraries for what we're going to be doing. And if you go to R, let me show you. So you would. This is the RMD file that I'm using to create that HTML. And what's nice here is that you can, load these things. So for example, you load these libraries by clicking run here. These are our code here in gray. And then next, okay, now we're, the libraries are loaded, but what about the data? So let me tell you a little bit about that. And I hope this is not obvious to all of you, but basically, when you write a paper nowadays, you have to turn in the replication code, how you got your results. That was not the case before. When I started out, you would just send the paper and that was it. And you would have your tables published. But then obviously some people pointed out that people could just make up numbers, right, at that point. And you were based on trust. And with the advances in computing and storage capacity, we just moved to a different model. And now when you write a paper, you basically upload the data, to the extent possible that you used and your analysis code so that people can replicate it. And so I think for the younger generations, this is a huge thing. This changed over the last couple of, 2, 3, 4 years. And now a lot of the, at least in economics, journals now have replication, ask you to submit a replication package, okay, alongside the article. So that's called the DAA. At the AA, American Economic Association, your paper is not accepted until the data editor accepts your replication package. Okay, so let me show you. I'm going to my web page here at ARE and see. I'm going to the 2018 Subways and Urban Growth paper, and you can see these links here. One is a subway lines tutorial, which is this one that we're doing today. The other one is the Radiance Calibrated Nightlights tutorial. So the address is ARE. Let me put that on the chat. So you can download, you have the paper there, the PDF, and then you see this replication files. I'm going to click on it, and where it goes is this repository of the data and the replication files. So this is hosted permanently. It's not on my website because I could disappear. My web page could disappear. But in these depositories, they are hosted permanently. Okay, so even they have a DOI, a digital original identifier, and you can cite it. You can say I downloaded my data from that that source, and that's stable. And so most papers have this. So let's go to the AA so you can see this. So if you go to the American Economic Review, for example, and you see the current issue, let's see, monopsony in the US labor market. Okay, so that's the article. Here you have the PDF of the article, and then well, I don't see the replication files. Maybe it's not empirical. Maybe this one. Let me go to mine. So for example, here, sorry, that's the article. And the replication files, you go to the AEA's, the American Economic Association repository for data, okay? And similar to what I was telling you, you have the replication files for this other paper, and then you have the README, which is the instructions, then the data that I used, and the do files. And that should be basically pretty widely available now for any empirical paper. Of course, it's a theory paper. There are proofs in the appendix or whatever, but that's not empirical. All right, so that's a huge thing that I feel has changed. And you can just download, here it is, for the current paper, you can just download the data set from here. So here's a zip file with replication data. And so if we click on that, I already did that yesterday, but you know, if we download it, here. It's in a zip format. You can unzip it, and what you get is here, this replication file. Okay, so you have data, output, and a do file. In this case, it's a stata, as I was saying, it's a stata do file. So here, let me open that up so you can see. And you can just run this, with the data set that is uploaded. You can download that, and you can just click, you say execute, and it'll create the tables. But what's nice about this is that you can see how everything was defined, starting from usually if it's a publicly available data source, it's just basically from how you download it, how you cleaned up the data set, what analysis you ran, and what the tables look like. And that's what these files do. So for example, this one, it's creation of the data set. Now table 1 for descriptive stats, these are the mean, etc. And then the regression tables and the figures, it's all here. So what Natalie did is she took this and then turned it to R, basically, which is the open source. Okay, any questions there? We're good. Is everyone good? All right. Excellent. All right. So that's the replication file that's freely available for you to use if you want for this. And then, so let's go back to our markup. So, yeah. So now we downloaded. So we're here. We download the subway stations data set. We separated out what we call subway census, which is the other link there. Here, there was the replication, and then the subway census, which is just the subway station, just the pure subway stations data set, historical series of shapefiles with subway stations worldwide, and shapefiles of subway lines as of 2010. So that's separate, just in case people just want to download the subways archive. So that's this one. Okay. And so we have I assume you downloaded the data set, and now we're gonna use this with R. So we can basically read, see here, we're using the geospatial tool. We use this command stread, we give it the path, and notice that this is a SHP, so that's the ArcMap architecture for these georeference data sets, either vector or raster. This is the projection system that we're using. So, these files are just points, and then some features associated to those points, and you give it a projection. What kind of map is using, assuming when you project. So when you do that. Let me go to RStudio. So when we do that, we read the shapefile. It says, okay, I was able to read the shapefile from Esri, right? And so these are just the geometry type is points. So XY. Remember, this is the latitude, longitude from Google Maps, right? So this is just now projected, so we can think of it spatially. You can think of distances between the points. We can draw disks around the points of the subways and calculate things like how bright is it around a subway station? Does it become brighter? All right. We can then, next point is we can show what that data looked like in the background. As I said, the alternative is for you to use QGIS, load the shapefile as a layer, and then open up the characteristics of these points. So it'll have associated to each point, right? What the shapefile does is it has a feature, in this case a point, which is the location of subway station. It'll have attached to it a DBF file, like a list, like a CSV, with the city name, the country, the year of opening, etc. And this is what you're observing here. So now that it loaded when R loads the file, it can give you, show you what the data look like. So we have the following variables. So we have, this is the projection system, WGS84. It's based on that code that ArcMap developed for different projection systems. And then it's points, and basically the continent here for the first few ones, we have South America, continent, our country is Argentina, the city one is the variable with the city name, it's Buenos Aires, and then it's associated urban code, which is coming from the population data set from the UN, okay? So it's a unique identifier for a city. And then this is our undergrads who wrote down this data set on the subways. The name of the line, so in Buenos Aires, it's line DBA, that's the name. This is an auxiliary variable, line name underscore at the end, just in case, basically sometimes you have, like in New York, you have lines that are like a Y, right? So you have a straight line, but then at the end, you can have two branches. So what we did is we gave it a slightly different name for one of the branches. So that's kind of just to draw the maps better. This variable is used for that and for those complicated cases. Loop is whether the subway line is actually on a loop, which when we draw them, it's going to be different if they're loops. Usually they're straight lines, and so you can just connect the dots, and that gives you you can draw the subway line. But if it's a loop and you draw the subway line, you can look funny. So to detect those, you do that differently. We basically kept track of whether this was a loop. Some subway lines are loops, like I know Moscow has one, I know Tokyo has one, etc. Okay, so it's one if it's a loop line, and then we have the station name, and then we gave it, this is again for our purposes, like a full name. So that's just a concatenation of city, name of the station, and name of the line. Okay. Yeah.
Again, so what is the loop variable doing at the end? Like how?
We used it when we drew the subway maps, the subway systems, because the algorithm that we used to connect the dots was, if you have the same line name, we basically did, I think, shortest distance. So we kind of connected to the next, you have a sequence of XY points in space. And so we connected to this one, which is the closest line. So then we drew the line to which one is the closest one. That's not the previous one, etc. And that's how we drew the straight line. But if it's a loop, it's different, because then it starts zigzagging. So we used a different algorithm for that. Does that make sense?
Okay, yeah.
So that was it. It was just a technical thing, because we saw that for the algorithm for the straight line subway lines didn't really work when we drew them. And why were we drawing them? Because we were thinking, we were describing length of the subway line, for example. So that was the reason. Okay, and then we have the station ID, which is just a tracking number of those station IDs. Terminal is another one that helps us with the algorithm. It's a 1 if it's an endpoint, because then you can start at one of the endpoints, and as I said, go back to the non-endpoints to draw the line. Yep.
Do you attempt to distinguish between locals and express trains, and where some stops being skipped?
We did not. I mean, to our knowledge, only New York had that. So New York is a pretty special subway system with that system that I know of, but it was pretty rare. And yeah, we didn't, based on the data sources we collected, we can't know if it's an express line, right? We could have for New York because it's documented, but at some point we thought, well, it doesn't really, it's not gonna play a big role because it's not that common, right? New York is amazing in that it has four tracks, right? A subway line has 4 tracks, which is quite unique. Most places just have 2 going and back. This one has for the locals and the express. So those guys were visionaries.
I mean, you might see locals with a different brightness around the local stops versus the
Probably.
hang stops.
Yeah, that's right. So we ignore that, basically. Yeah, that's a good point. And we have to confront that. And, yeah, that's the stuff you have to decide when you're doing an empirical paper. All right, so here we kept the year completion, which is what we're going to be using for the drawing. So you can see in Buenos Aires that this subway station was completed and became operational in 1937, 13, etc. So they had a pretty old subway system. It has kept, even though Argentinians don't recognize it, it has been growing little by little, but it has grown. Most of it is very old, but yeah. All right, so this is the subway lab, subway lung, and so that's what the subways data set looks like. And you can use it for other papers. We basically wrote the other paper I was telling you about that we wrote and that was published this year in the AJ Applied was using this and then merging it to air pollution variables from satellites too. So do subways make the air cleaner? And there we found out that it does make the air cleaner. Okay. If it's a highly polluted city, that's the only caveat. If it's a very clean air city, like, I don't know, Copenhagen or something, and you build a subway, you don't get cleaner air. Okay, so it is for highly polluted cities, that result. Okay, but basically, you can think of a lot of stuff you may want to do with these subways data sets. Okay? And now you can just download them and use them and save yourselves a lot of time. They're obviously not updated. So this paper ends in 2010, the subways and urban growth. The subways and air pollution, we updated it to, I think, 2018. But if you do something now, there's 5 years worth of more subway construction that has been going on. You would think about. Okay, so I guess let me show you so that you can see how we did it. I'm just going to pick one from so you can see how we collected these with the Google Maps. See, so if you click, this is, I just took one of those XY variables. Now I'm showing you where it's going to, but what we did was reverse. We looked at the map. So this should be Buenos Aires. And you can see here, it's marked as the Olleros subway station. It's going underground. So it helped us in this case, right? That the Google Maps had the mappings of those, right? Of these, the Jose Hernandez subway station. And you can see pictures of it, right? For example. So we're okay, that looks like this looks like a subway to us, it's electric powered, etc. Right? So that's what the undergrads were doing to give us each one of those XYs. And this one, I mean, was easy, but some of them are hard. And they're less well documented. Like, we did have an RA that knew Farsi, but it's hard to read those. The dates, etc. They have different numbers in Iran. Okay. All right. So we have so this is, now you know how we built this, the subways data set. And now let's use R to visualize what one of these subway systems look like. So we're going to select a part of the subways data set. And so we're going to filter if the variable city one is Athens, so you have all of the 180 or so, or 150 cities with a subway. And then we're gonna plot using the XYs, what the subway map looks like. So this is what those XYs look like for Athens. And one of the things I'll mention here is it's really interesting because when you go to a city and look at the map of the system, it's very distorted. Like it looks nice, you can fit it on a page like a square. But the distances between the stations don't look at all like what they look like when you georeference them. So that was kind of a surprise to us. And actually, there's a really cool paper by Ferdinand Rauch saying that actually in London, because people look at the map, at the tube map, and make a decision of how to go, they may not be aware that they're not taking the shortest route, between work and where they live. Because on the map, it looks like this might be the shortest route, but in reality, the station distances could be pretty long and very different from one to the other. Or the distances between stations, if you were to walk them, for example, they're not obvious at all from that map. So what he does is he uses this. There was a strike in London a few years ago where they shut down, they were undermanned, so they shut down a bunch of the stations. And that forced people to experiment because they didn't have their usual route. And what he finds is that actually when the strike ended and all the stations went back to normal, people had changed their commuting decisions. They kind of had learned something new, so they were under optimizing. And they think it's because of the distortions in the maps when you draw them on that.
So on the maps, what usually happens is that they make the stations distant between each other, or?
Yeah, exactly. They make them so that they fit right nicely like that. But the distance between stations could be quite different. They might be not equidistant. Typically, what happens is downtowns are much closer, and the outer parts they're much further apart. Let me see if this one works. This is the BART for us. So you recognize it? So we're here, Berkeley somewhere. This is pretty tight around the downtown San Francisco, which is what I was saying. And then they're much further apart, in the outer part. So look at the station between these two, the distance between these two versus here, right? And when you see the drawing, that's not the map you see, right? So anyways. All right, so that's that's basically R with ggplot being able to show these. We can make this nicer. In the tutorial, you can actually download from this source GADM a background map to contextualize these dots. We don't use that in the paper, so I'm going to skip that. But basically, you can make this nicer, like you can add colors, etc. And there are tools in R to draw these nicely with point and click, or you can Google these. So if we use ggplot, we're showing the X and the Y's for, in this case, the San Francisco subway system. Sorry, I still kept the label Athens, so that's no longer right. Anali would kill me. Let me go back and call this one Athens. So now we have this, we're going to call it subway Athens are these points, but now we make them nicer. So we add colors. So each line looks different. So we have line 1 is the one in red, line 2 is the one in blue, and is the one in green, and line 3 is the one in blue here. But now you can see a map that makes a little bit more sense, right? So this is the code for that. And give it a title, and then the color scheme for the different subway lines. Okay, so that's a nicer graph. As I said, all of this you can do in QGIS too. All right, so that's our first data source, the subway systems. Now, those are the dots, right? That's the source data, but then we drew them, we created lines, And so for that, we can download this other, let me show you. If you download the subway census V1 zip file, you'll see there's a station points, which is what we just used. Then we have the route maps that we work with. So these are basically, you can draw like an evolution of subway systems every 5 years. What they look like, what do they look like, what do they look like? Okay, so you have a sequence of these up to 2010, and that's what we're going to be drawing now. Okay, and then there's this ridership data also that we collected. You can also download. All right, so just going back there, that's the one we're going to load now. The route maps, as I said, you can have what subways look like since 1930 or something. We have there up to 2010, and so we're going to read again this shapefile data, the SHP subway map for 2010 with this projection system, and so now it was successfully read. So now it's loaded in R, and these are lines. Okay, so there's basic 3 geometries in vector. There's points, lines, and polygons. Right. So this is another way of but the underlying source is the same. Those XYs with the subway stations, but now we're going to join them, and this is what they look like. Okay. Now, because it'll make things easier, what we're going to do is this is just the, has the urban code and then the line, but we don't have the country name, year of opening, etc. We can merge those 2 data sets, and that's what this step does. Is it will join, well, in ArcMap we call it join, the shapefile with the subway lines, right? That's a feature, and we have an urban code. So we're going to join it to the table with the continent, country, etc., using urban code as a joining variable. So this is how you do this in R. So you write, we're going to call it, give it the label urban code info. We use the subway stations data that we defined above. And we're going to keep the variables continent, country, city, and urban code. Okay, so that's step 1. Step 2, we're going to join it to the subway lines shapefile. And the way we do this is we'll give it the label subway route 2010 add, and then the special thing you're using here is the merge subway route 2010, which is what we loaded using the urban code by urban code. Basically, that's the joining operation, and then we're going to ask it to show us the first 10 observations. So there are three steps. And so here, it's successfully executed, and now we can see that the subway lines. Now we have the urban code, the continent, the country, the city, okay, and then the line. Okay, so that's useful.
The only new thing on this one is the last column.
Or the other, we loaded this first and then joined these variables. Okay, right? Okay. Well, that's great, but now let's draw it, right? So again, we use we're going to be using the plot. So we're going to be doing the following. We're going to call it Athens route 2010. So we have this what we call subways route 2010 add, right? This joined data set, but we're going to filter on the city being called Athens. Okay, so and then we're going to ask it to plot the Athens route 2010 geometry. And so this is what it looks like. So notice these were the points. So basically what we did is go from here, right, the XY into subway lines. Okay. Does that make sense? You can draw these with color, etc. So yeah,
You probably don't know the answer to this, but I'm getting a weird error where I can't load shape files and it says the source cannot be corrupt. Source could be corrupt or not supported. The ST drivers or list of support points. Has anyone gotten such an issue?
Updated my RStudio and then I set the working directory to work.
Yeah, it can see the file for sure.
I had the similar issue yesterday, and what I did was download the most current version of RStudio.
Okay.
Because when you load the libraries, if you're not using the most recent version of RStudio, it can create these issues.
Gotcha.
That was my solution.
Okay, yeah, sounds like a similar situation. Thank you.
Okay, so but basically, what we were doing is just displaying this root maps shapefile, one of these, right? So we have these for many years. Let me show you in the presentations we did for this paper what it looks like. So here is together with the night lights data, but you can see this is Shanghai. And in 1995, we're drawing the subway lines for Shanghai, filtering here, focusing on Shanghai. But you have one subway line. This is the river and the coastline. We just added that to make it look nicer. That's not, and then you have the night lights data set that we'll discuss in a few minutes. But basically, the night lights is a raster data set with whiter is brighter. Okay. And so we're asking them in this paper if cities that grow their subways become bigger. And visually, you would see that as an expansion of the white areas. And Shanghai would kind of fit the bill, right, in a way. The other thing you see here are these circles that I'll discuss in a moment. So we're going to be calculating the gradient of these night lights by looking at the average value of these at different distances from the city center. Okay. So that's 1995, and then what I'm going to do now is show you the different these shape files at different points in time. So now we have 2000. So let me go back and forth. By 2000, they had built this is a pretty major system by now, right? Like 8 or 9 lines, and you can see that the lights. This is one issue with those night lights is that they're imprecise. This is the year 2005, and then this is the year 2010. So now it's by some measures, one of the biggest systems in the world, Shanghai, over the course of a couple of decades. But you can see now these lines reaching out to these urban areas, right? Kind of like the BART does here. These are pretty far out, but you can see it connecting these areas and how they light up, right? Let me go back and see that quickly. That was Shanghai in 1995, 2000, and 2010. Kind of that's what we were thinking of when we wrote this paper. Is like, wow, if you want to grow like massively, like Shanghai, how important is it to have a subway? When you see the people who argue for subway systems, they kind of give these types of stories, right? Like, if you want to be a world-class city, you really want to have a subway system. That's what they feel. A place like Bogota today, like, why don't you have a subway? So it kind of observationally that looks plausible, right? That to grow you would need a big subway system. But the paper's answer is no. We don't find that you need doing all of the analysis, we don't find that subways are required for cities to grow very big. And there are counterexamples, right? I suppose you can pick like LA is a massive city that only recently started building a subway, right? Houston is a pretty big city, no subway. Some of the biggest cities in the world, like in Asia, like I believe I may be, I'm going to say a wrong name probably. Delhi might not have a subway system. It has more than 15 million people. Nowadays, they're all kind of getting into it. But doing the analysis of whether the city could really grow really big without a subway system, the answer was no from the data. Okay, so that was the takeaway of the paper. But the second thing we did find is that the cities do look different with the subway. They do seem to decentralize, which is what we'll do next with R. Yeah, and sorry, your name?
So
Tom, okay,
it's amazing how quickly they were able to build out that subway.
yes, very
in a short
amazing.
Period of time. I wonder, relating that to the politics of various countries, it might be an interesting experiment to just see what kinds of countries are able to do that versus, because that could never happen in the Bay Area, for example. They want
That's right,
them to take years, decades to do things like that.
that's right, that's right. Very, yes, this is fascinating, the politics around the subway. I know there's some work out of MIT talking about these issues, the politics and the coalitions in democracies to get these things to work. So I'm blanking on the name, I'll come back to it, but there has been some work, but because this is really interesting, the politics behind it. How do you finance these? There's the issues of eminent domain, of course, but a big one is how you finance these. What we find, there's very little data on this. Our intuition in the paper from the few places where you can read about this, like where people have written papers or thesis on it, is that subways require massive subsidies to be built. They don't tend to be, it would be very rare for a private sector company to build a subway system, okay? So this is not like they're privately viable. So you could think, okay, there are all these frictions to assembling the land and permits, et cetera, so that we may want to subsidize that. But even the construction usually requires like federal government, subsidies. And then the difficult part is a lot of these are not even financially sustainable with the ridership once they're built, right? Once you have the capital cost in, the operating costs tend to be bigger than the fare box revenue. One example is Miami has a heavy rail that no one uses. It runs and loses a large amount of money. And that money, we think, maybe could have gone to, other stuff, right? Like the police or better schools, and it's not. So, it's not an obvious thing that you, first of all, that all subways are successful. No, we see a bunch of cases where the ridership is really low. Like in Spain, there are subways that sometimes have 3,000 riders a day. There are examples there. So I think the Chinese is kind of a successful from various metrics. They're pretty good at building subways that people ride, that are safe for people to use, and people tend to use them, and etc. But I would say that's not the case all the time. And it can drain resources from other uses. So even, for example, the Mexico City subway, it's half of it is fare box revenue. The rest is city resources financing the electricity, the maintenance, etc. Yes?
I'm just gonna ask, do you know if there's any literature on how maybe subways getting there's a relationship between nightlights and subway systems, like density within cities increasing due to access?
That's what we're going to answer next. Partially. I think you'll like what we do next. So it's a surprising result, okay? So we were surprised, but that's what it's pretty clear in our analysis. And you can read the paper for the details, but everywhere we looked at it, we couldn't find growth effects, overall growth effects, either in population, which I'm skipping here, or in the nightlights. Okay, so both pointed in the same direction. Minimal reaction of population and nightlights when you build a subway. Some cities grow fast and they have they're following a dynamic. You build a subway, it doesn't change very much. Okay, so here, let me show you some of the graphs, just to tell you what we're talking about. Yeah, so for example, here's a list of the biggest cities in the world by population. So Tokyo, Delhi, Mexico City, and New York, Sao Paulo. And then you have places like Mumbai that have no subway, at least until 2010, okay? And they have 19 million people. So Dhaka, right, 15 million, no subway. Even in, Los Angeles has a subway now, But, most of its growth, when you look at the dynamics, the period of really high growth was much before the subway. It's kind of, the subway came later. So that tells you something about whether the subway causes growth. The answer is no. We do see that big cities build subways, don't get me wrong. We just don't see them causing growth, okay? So you see this here in this graph. This is population size and whether the probability that a city has a subway at that size. You can see for rich countries, basically all cities in countries above 5 million, cities above 5 million people have a subway in the rich world, okay? You get about half probability of getting a subway in a rich country city when you're about 2.5. So at that rate, you start adopting subway as a transportation system. In poor countries, it becomes much later. It's just much later. It's something that's much more expensive. Only cities with above 20 million people do you see them 100% of them having a subway in developing countries. Before that, you have cities of 15 million or so that have half of them have subways. Okay.
Then,
Yeah.
When you have the nightlights, how much is it like?
And sorry, remind me your name?
Pedro.
Pedro, yes.
When you are looking at how, if you go back to the one you were showing us in Shanghai, you can see that the lights, like at the end of 2010, it connects to some areas, but those areas were already showing lights.
Exactly.
So, like, how do you address this? Like,
How do you get at the how do you isolate some exogenous variation, right? Is that what you're asking?
no, like, is it like the population driving the subway going to there, or the subway increasing the population?
We find that it's mostly a place grows, then you build a subway, more than you build a subway and then the city grows. That's what the data suggests. And we use this technique called instrumental variables, which is something that, think of it as kind of helicopter dropping a subway somewhere and seeing whether that place grows more. That's kind of the idea for this instrument. And we don't see that places that exogenously get subways grow more. So that's kind of the instrumental variables technique. As I said, we do this in many different ways, among them the instrumental variables. But this is a typical graph. This is an event study graph. So this is 20 years before the subway starts. And these are averages for these cities. This is population data. And this is the rate of growth between every 5 years. Okay, so if you want the annual growth, you would divide this by 5. And what you see is in T0 centers the year in which the subway system started. Okay, for our sample, which is the sample of all cities with subways, basically. And what you see is cities tend to grow faster early on. Then as they grow, they start slowing down in terms of growth, rate of growth. Then when you build a subway, there's no going back, there's no flattening or anything we could see. It just keeps on going. The same trend of decay, and reduction in the rate of growth of the city. If you trend that, you find a 0. And then if you look further out, this one is a non-constant sample. But even if you look 60 years out, again, the same thing shows up that there's no real, we don't see it becoming getting any kick in terms of growth rate of the population. Ariel?
So forgive me because I haven't read this paper, but like, how do you differentiate between like cities and metro areas, or like,
Yeah.
like how do you?
Great. Yeah, the
Figure out
UN
where the
basically has a definition of a metro area. It's not admin boundaries. So for example, San Francisco, Oakland is considered a single city in the UN data.
Okay, and that's what you're using.
Exactly. So we use metropolitan area. The reason we like the UN data set is that they use the same definition in different parts of the world. Because usually what is a metro area varies quite a bit by country. So what we call a metropolitan area here is using a particular definition, and then in Canada, it's another one. And so we can't just compare what each country calls a metro area. You really need to have a single set of people looking at the same source data, which is census data at the census tract level, right? And then aggregating it to what they think is an urban agglomeration.
Yeah. So
And
it's
it's-
like, so when you say city growth rates, you're talking about these UN
Yeah.
metro areas?
Yeah, these are the
So
metro areas.
Yeah.
It's not San Francisco City, it's like the Bay Area.
Yeah.
And the LA, with the Inland Empire, that's considered a single area,
Yeah.
et cetera.
And so you're taught when you say growth rates, it's like, I don't know, just trying, the
Yeah.
second part is much clearer to me, where you're like looking at what happens to the structure of the city, but like within, like, because the city is so, the match between the city and the subway, I'm struggling to like figure.
Yeah,
out.
no, you're right. Typically, that's something that you see when you compare the night lights with the subway maps,
Right,
is that the density of subway stations is really high close to downtown. As you move further out, the likelihood that you're near a subway station just falls dramatically everywhere.
right.
And subways really require a dense amount, densely populated areas to function. And what that means is that you provide a lot of service to downtown or to get into downtown. And so one of the things we see in the maps is that when we think of why urban areas grow in urban economics, we typically think that the growth occurs at the margins of the city, as you turn farmland into urban area. And that process may be pretty uncorrelated to the subway system, right? Which is basically serving people who live downtown. So that might be, if you want a city to grow, maybe your best bet is to build, streets and sewer and water, right? And subways are not really the best way to make a city grow, or at least we don't find that. But yeah, so, and as I said, there's this competition of resources, right? If you have a subway, you may not be able to provide those other public services that might allow for faster growth, like schools and things like that. With typical financing rates, from what we learned, I think London is the one subway system that's mostly self-financed, like viable financially, and it only covers about 90% of its operating costs. The other, as I said, some cities is a disaster in terms of how much revenue they generate. So those are basically depleting local coffers from other stuff. Now, the deeper question we have is in these series of papers was, okay, if you're going to subsidize a particular form of transportation, there should be some externalities associated to it that we all enjoy. So we should pay a few of us to use the subway, right? That's what we're doing with the subway system. Some people are using it, they're getting subsidized. And the question is, what do we get? What does the rest of society get in exchange for doing that? And so that's what was interesting about the subways and air pollution paper, is that we do see that cities benefit from cleaner air. So that might be a reason why we may want to subsidize the subway users, because we'll all get cleaner air and less congestion, which is a paper that Michael Anderson here wrote. So when there's a subway strike in LA, you see congestion and the highways going up substantially. So you get more pollution, but also worse traffic times. Okay. Now, okay, I'll stop there. All right, so let me go back to our studio. So we saw basically what we did with the subway lines. There's this third data set that we use in the paper, which is the ridership. This one's even more, it's less comprehensive. So we got, not every city publishes data on ridership. As I said, sometimes they don't want to because it's shameful. Other times, just some places are disorganized and they don't publish these things. Sometimes they are not published, in quite enough detail. For some places we had to go through like newspaper articles with, where the administrator said, yeah, this year we had X, and so we kind of try to see if we could generate data on that way. But basically, for maybe half or of the cities, is that right? Well, no, I don't recall now, but for a good chunk of the cities, I would say maybe at most half, maybe less, we had ridership data. And what was interesting to us about those ridership data is sometimes you did have broken down by buses, buses, subways, and overall. And so we can do some analysis with that. And so one basic question that people have when you build a subway is, the tractors say, well, if you build a subway, the people who were using the bus before now are going to use the subway. So you didn't get an increase in transit use, right? Those people they didn't have cars. They were taking the bus, and now you build this fancy new subway, people stop using the bus, but you may not get an increase in total ridership. So that's one argument that has been levied against the building of subway lines. And you see this, for example, in LA all the time. They are building a subway system, and you see the detractors saying, well, and I mean, it's not unjustifiable, but they say, if you build one more subway line, the bus system where the really poor people, going into the neighborhoods, they really rely on that. And you're going to basically substitute that for a subway line that's going to serve very few people that live, close to the subway station. Then, sometimes the disadvantaged communities leaders sometimes argue against the subway for that reason. So this is a question we try to answer with these data. Yes?
There's probably a relationship between the level of traffic congestion and the advantage of building a subway. In other words, like in Manhattan, for example, the subway is going to be faster than a bus because it's just so much congestion or difficult to access. You've got just a few bridges going to Manhattan, you've got the island.
Totally.
Going to Manhattan. So you want to do the subways because it's so much.
Yeah, and then, the way I see this is, it's interesting to do an analysis like this for the worldwide subway systems. What happens on average? It helps us think about each individual case. I do think New York City is very special in its context, right? It's an island. It needs to bring in a lot of people in the morning, and you only have a few bridges or tunnels. And so this definitely seems like, like it made a lot of sense for New York to build a great subway system. And so they did, and the city thrived, right? Maybe that wouldn't work in a place like LA, where you already have a bunch of highways, and it's hard to actually attract people to the subway.
It's interesting to look at the effect of the subway expansion at the end of the 1930s to Long Island. It just caused a huge expansion in Long Island property ownership and construction. Because they want to get into the.
Totally. There are, I would say there's a lot of papers to be written, right, about these, now that we have amazing satellite data that can go back in time, or even the UN population data, you could do a lot of these studies. I'll mention, the literature in urban economics before this paper was about using recent subway line expansions, for example, in London or in the US. And what they found, they looked at property values and do find a reaction that places that get a subway, like houses that are close to a subway, are increasing value by about 5% per square foot. In percentage terms, it goes up by about 5%, the values. So people do value living close to a subway station compared to living in the same city, but far away from the subway station. So those what those papers were doing. But you're right, like looking at the urban transformation of places like Staten Island would be great. I haven't seen that. Yeah. Okay. So here what we're doing is just showing you this table, which is just a CSV table. You can read it with R. Here, read the DTA. So this command, read DTA, is helps us read data sets, which is nice. So into R. And so what those look like, as I said, is the urban name, the urban code that links all of these three maps, three data sets, country, the year for the city, and these are total ridership, right? In these different subway systems for which we have data. So let me do a little bit of analysis here. So here we're going to create a table of summary statistics. And so this is the code we're going to run. And so these are a few steps. So year one, we're going to call subway stations pre-2010, and we're going to calculate the number of stations and lines by city. And then and we're going to summarize here the number of distinct station IDs, right? And then for the lines is the number of distinct line names. So that's going to tell us how many subway lines are in each city, how many stations does each city have. Okay. we're gonna calculate the mean and the lines by continent. So we can do the same thing, basically group by continent, and then we summarize the cities that have a subway system, the stations in the continent, the total, the mean. So you hear the sum, mean, and then total lines. So you summarize the sum of lines and the average number of lines in a city. Okay, and then we and then in total. So this is, you know, we're not grouping by continent or by country, and this is the total. We also calculate the length of the subway lines. So this is a cool step, right? So here we call on the city stats routes. So remember the shapefile with the lines, the lines of the subway lines, and we can summarize in R the length of those lines. Okay, so that's what this step is doing, and then in this step we calculate the average length of the subway lines in the continent and the sum of subway lines in the continent. And then finally, the overall, the sum for the whole world, and in terms of the number of kilometers of subways and the average number of kilometers in a subway system. And this is where we use this table, and let me run this for you. So that's what we're doing here. Basically, calculating a mean, basically a table of summary statistics with R. Okay, so. And it's quite amazing, right? Because it's going through the shapefile and calculating the length of the line. And it's going to give us the average, the totals. Okay, so this is what this table looks like. It's very similar to the one in the paper. So here you have, we calculated the total, we calculated by continent, and we have the following statistics in the column. So total cities. So what this says is that in Africa in 2010, there was one city with a subway, and that was Cairo. Okay, and you can see the inequality here, right? Like the continent of Africa had one subway system, and Cairo is a massive city. Asia, 34 subway cities with a subway. Europe, 51. So this is a very European phenomenon, the subway lines, subway systems. Middle East, 8. North America, 30. South America, 14 cities with a subways, for a total of 138. As I said in the more recent papers, it's closer to 200 cities with subways nowadays. So it's been growing pretty rapid. All right, how many stations exist? So as I said, it's about 8,000 stations worldwide. And the big players here are Europe with 3,000 subway stations, and Asia with 2,500 stations. North America, 1,600. Of these 1,500, I believe New York City has about 400 stations. It really dominates the U.S. It's such an outlier in the U.S. The rest of the systems are quite small, except Chicago has a reasonably sized system, but about 60 stations, I believe, if I'm not mistaken. No, maybe more. But New York is like the biggest one. I think the biggest by number of stations in the world. But as Tom was saying, a lot of those are local, right? And they're really close to each other. It might not be the same as me. Okay. What does the average system look like? So what this says is that in Africa, the Seoul system has 51 stations, right? This is average across the cities and the continent. They're not so dissimilar, right, in size. So in Asia, the average subway system has 72 stations, 61 in Europe, 22 in the Middle East, 53 in North America, 34 in South America. In terms of total lines, this is the number of subway lines. There's about 500, and again, Asia and Europe dominate. What is the average number of lines in a system? So this is in a metro area. So Cairo had 2. Asia has an average 4 lines. Europe, an average 4 lines, North America, 3 lines, South America, 2 lines, okay? And then in terms of route length, they're about, so, this one's simple to think about. Basically, Cairo has 59 or 60 kilometers of subway, right? If you count the distance you can travel. And then on average, again, the average here is for one city, so 59. But in Asia, it's 101 kilometers. In Europe, 64 kilometers. And then North America, 64 kilometers, okay, of subway lines on average. So that's what those systems look like. So that's the description of that. Any questions or? All right. Cool. And now to give us a feel of the data, we can do the summary stats using this command cable with K for just Greece. Okay, is Natalie from Greece, or why was the example of Greece and Athens? Do you know, Sam?
I'm not sure, actually.
That's interesting. Maybe she loves Athens or something.
Yeah, maybe, well, she was a classics major.
Oh, maybe that's why.
So it could be that idea, yeah.
So this is just those same stats, but for the country of Greece. And so so Athens had a subway, and with 52 stations, 3 lines with an average length of 51. We found that on average, the distance between stations is about 1 kilometer. And actually along that dimension, the BART is quite an outlier. Like the distances between stations is super big compared to the average. Okay.
Isn't it technically commuter rail?
Is what?
I think it's commuter rail.
Yeah, it's a mix. Yeah, it's got characteristics of both. You're right. Yeah. All right. So what about, we can do the same, a table with summary statistics of ridership. So that's using the ridership 2010 database we loaded. We defined it up here, right? When we here, let me go here. See, we called it ridership data. And so what we do here is we're going to call ridership 2010. It's going to be basically the ridership data set that we defined above, just for the year 2010. Okay. And so we're going to calculate for that set of observations, ridership 2010. We give it this label, subway stats 2010, and we're going to give the average ridership, the standard deviation of ridership, and then number of countries and the number of cities. And then the same thing for subway and bus. Okay, so we do the same for buses. And what we find is this is the average number of rides in a subway system in a year. So if I'm not mistaken, that is on average. So on average, for the countries for which we have data, the annual number of rides is 376 million rides on the subway, okay, for the average, for which we have data, which in this case it's only 77 out of the 150 cities. For the bus, look at, I mean, I don't think a lot of us realize this, it's also a major player. For those that report subway ridership data, it moves around 241 million rides. So, and so now we can go to the question, oh, is that right? Well, let's visualize this. We're gonna get to the question of whether substitution, when you open a subway, do you see reductions in bus ridership or not? So now we're gonna do this chart, which is also in the paper, which is, let's plot what's been going on. This is, I think, the first graph, the number of stations over time. So we start out with the first subway system in 1850 and up to 2010. And so you can do this with the following command. We're going to summarize the number of stations. So that's the number of distinct station IDs, and we're grouping them by year of completion. And then we can plot these with the plot command, okay? All right, so when we do that, this is the graph you get, operational stations by year, and you can see this acceleration it's continuing because the world is going through this urbanization phase, right? And so we're getting more and more people in cities and people are using the subways. Okay, so we're gonna do a quick regression analysis of the ridership. And so the question we have is, does opening more subway stations lead to more public transit ridership or not? And as I was saying, do we observe that if you build more subways, do you observe less people riding the bus, for example, right? Which is the argument that has been made for LA at least. We've already gone through this. The data set and the replication files is here at that Harvard Dataverse I mentioned, that repository. I already downloaded it, and it looks like this. Let me go up here. So this is the subway census, which is one of the files in the replication Dataverse. The other one is in the replication file. So this is for the paper that creates the tables in the paper. The data we have here is just well, I can open it up. This is the data set that it's in Stata format. We're gonna read it in R, but this is what it looks like. So we have urban code, year, the name of the city, in this case Kabul in Afghanistan, longitude, latitude, and other control variables like kilometers to a river, kilometers to the ocean, and then these are the variables. Well, I'll go over them with the lights. Oh, these are highway kilometers at various distances from the city center. What else? We have number of subway stations over time. So basically we turn those X, Y's and year completed into a panel of a city year. And we know how many stations they had. So in this case, Kabul has 0, right? DOP is a change in operational station or operational stations here. Let me go to, yeah, so that's what the data look like when you download that. And so we're gonna load that database that I was just showing you, but we're gonna load it in R. And that's, you read the DTA, the Analyze Me DTA. So it's loading. And now once we have that data loaded, we can do this analysis of whether when cities build more subways, what happens to total ridership in public transit, and in particular in buses and in subways. Okay, so now that's loaded, and we can create a regression table. As I said, the dependent variable is going to be the change in log ridership, and the explanatory variable is a change in log subway stations in the city. In one of the tables, one of the main tables in the paper, I'm just going to be focusing on that one. We did this. We have a quinquennial data set, so we look at every 5th observation. Even though we have the subways every year, we can run a regression just every 5 years. Because you build a subway, but things will take time to get built, etc. So we could do that at the decennial level, or in the end, we looked at quinquennial. You can look further apart, but then you wonder, like, did whatever happened in the city, was it really associated to the subway, or was it something else? So in the end, we did quinquennial. So this is what we're doing here. So we're looking at every 50 years since 1950, and then we're going to transform the date variable because that's the data thing. It uses certain numbers correspond to dates, and so we transform it there, and then so that's the preparing the data set, and then then this is the regression command, this line. So this one is we're going to run a fixed effects linear model where the fixed effect is the urban code, and then we're regressing the change in log ridership for subway and bus, on the change, this D means change in log operational subway station. So operational, because sometimes you build a subway station, but then the service could stop. And so these are the ones that are in use in that year. That's why it's called, we call it operational. Using this rec data prep that you defined up here, right? These every 50-year observation. So that's regression 1, and then regression 2 is we just changed the dependent variable. Just this is change in log. This is change in ridership from from the 5 years ago, right? So that's the log ridership subway on number of stations. So you expect that if you build a subway line, you should see more riders on that subway system, but we don't know, right? We'll see. And then same thing for buses, whether, the critics of building subways at the expense of buses say that this will fall, right? And total will not change. People who believe in transit systems say, okay, no, build a bigger transit system, people will ride it, actually becomes more attractive, you have more stations, network effects, etc. So, so we have those
What
total.
were the zeros for?
That is the fixed effect linear model command. I think that's if you want to define weights and things like that. So it's just saying don't use weights. And then you just show us this in a regression format, which is using this. Oops. What happened? There we go. Is everyone online is going okay? All right. And so with the Stargazer library that we loaded, it just takes those 3 regressions and shows them in a nice format. Okay, so we do that. And this is what that looks like. So that's our regression table using Stargazer. It looks like some of the one of the tables in the paper. So we have a dependent variable change in log ridership for all, this total transit system on the change in subway stations. So this is an elasticity, right? Because this is in log and this is in logs. So this says that if you grow the subway system by 10% in terms of stations, then the ridership will go up by 7% in terms of riders. So it's not an elasticity of 1, it's a little bit less than 1. Okay, so but you do see significant increases in ridership in places that build subways. So on average, they are being used. That's what it's saying, right? And the elasticity is positive and significant. So building more subways on in the experience of these cities built leads to more reported ridership in the public transit system, which includes buses and subways. Now. 60% of that, so the elasticity of 0.57 is coming from subways, okay? And then no relationship, there's no perceived change in bus ridership when you build more subways. So we don't see that substitution that some critics were saying that, oh, if you build a subway line, and when you see a lot of the times when the cities build a subway line, they will reduce the bus service on those areas, right? And so, it's plausible that you would find a substitution, but that's not the average thing. We see no change in bus ridership when subway systems grow. You do see more ridership in the subway system. Tom?
Is there an attempt to adjust duplication of routes? In other words, if they build the subway, then maybe they shift the route of the buses and that sort of thing.
We don't have data on bus routes. That would be great. Maybe someone, some entrepreneurial person could do that, because nowadays, in Google Maps, I don't know if you've noticed, but they do have information on transit, right? And when you look at how Google Maps gives you that information, all they tell transit agencies is they say, please upload a file with your bus schedule and we'll report it in the Google Maps. So there's cities, what they do is they will create these very simple common format files. They need to be updated pretty frequently, but you do get, for well-organized cities that can be bothered to do this, you do have information on their buses. So you could analyze something like that. But if you go back to 1930s, forget, I mean, I have no idea where the buses in Buenos Aires were. So we couldn't do that. So we're ignoring that. And your point, Tom, it is, some subway systems, when they grow, they build a subway line, they'll typically reorganize the buses to feed it. That's one common thing. Or they'll move those buses to some other areas that are underserved, etc. Yeah. So, but we basically don't have that. We'd love to know that. So that's a great question. But nowadays, if you look at newly built systems, I think you could look at that. Like what happens to the bus configuration when the subway gets built. And no, to my knowledge, no one has done that. But I may be wrong, and maybe there's someone who's done that. All right, so that's kind of the ridership analysis of the paper. And now we can move to the night lights. So as I was saying, let me move here for that. It just looks nicer. We've done that. And now the night lights. Okay, so let me tell you a little bit about these night lights. So these are the DMSP OLS nighttime light time series, and Geo4Dev has a tutorial on those. So, and there's a bunch of analysis being done with those nowadays. And here's where I'm going to tell you how young people leapfrog the older people, and now I'm an older person. But basically, we downloaded the data, the source files from NASA, and organized them, and had to unzip each one of them, etc. But nowadays, and this is the tutorial that is, I hope Sam is going to put the link to it now, is you can use Google Earth Engine, and basically Google Earth Engine has those raster files on command. You can just use them when they have an API, and that's what that tutorial does, is using Google Earth Engine. You can just do this on, very quickly. You can save yourself, a couple of months of time compared to what we did, which was go to NASA, download them, organize them, and do the analysis. So nowadays, I think there are these neat tools for you guys to use, and there's a tutorial, and I definitely didn't have time to cover that, but I will show you the operations that were done in that tutorial, which are very simple. And again, that's one alternative, the Google Earth Engine, which can load, they have a huge repository of images, etc. It's amazing. I mean, that's what my students are using nowadays. And because that way you don't have to load these massive files onto your desktop, etc. You may not even, yeah. So, but that's not what we did. We did this in ArcMap, but you can do this in QGIS. But let me show you what we did quickly. So we've covered this. All right, so we have the centroids of cities. So in this case, look at Shanghai. These circles. Now we go to these green circles. They're faint, but you can probably see that there's a centroid of the city, which is coming from the United Nations data set. Okay, that's kind of the downtown. Not that obvious, but they created it somehow. We just use it. And so we're going to draw very simple. We're going to draw circles, disks of different radii around the city center up to, well, let me tell you that.
Question.
Yes?
Is that just the way this display is showing, or is the light data always saturated so you really can't see the variations?
So these are the every 5 years without the top coating. So these have no top coat at 63. They can go pretty high. So maybe the display doesn't show that. I mean, this was just for visual purposes, but the underlying data, these pixels, with the radiance calibrated night lights data, these are not top coated at 63. I remember seeing values of 270, etc. So you can really see more of this internal structure of cities. Okay, so what we do is we take the centroid, and this is again a very simple operation, and then we draw disks around the city center of different sizes. So that's step one, and then step two calculate the average light in those disks. With information on the average light on those disks, you can back out what the light is in each of these donuts. Just this basic, I can pull it up, but you basically, using the formula for a circle, the area in a circle, you know, the average of the big circle, you know, the average of the small circle, and then you can just subtract and get the average of the light here, the average of the light here in this donut, and the average of the light in this donut, etc. Okay, so what we do, does that make sense? So very simple operation. You can see how we can do this in Q or in R, or in the case of the Google Earth Engine, the other tutorial, they use Jupyter and Python. So Python is what we use for our GIS and QGIS. And so that's just an interface like the one in R Studio, but for Python. Okay, and that's so it was kind of too much for 1 2-hour tutorial. So I just went with R and R Studio. And as I said, I don't think, there are multiple ways around it. They're free. So one is ArcMap, the other one is QGIS, and the other one is what's in the tutorial, which is either Google Earth Engine or Google Earth Engine API feeding one of these Jupyter notebooks. Okay, so so here's what, in the tutorial you'll see this image. So this is Istanbul. And you have the circles to these disks around the city, and we overlaid the pixels, those like the one I was showing you for Shanghai. We calculate the average value of this. That's a simple operation in ArcMap. Okay, so what we have now, and we do this for circles of size 1.5 kilometer, 5, 10, 25, and 50 kilometer. For all of the cities in the database, okay, all the large cities in the UN population data set. So now we're gonna get to your point, Tom, about the gradient. Okay, so what we did is we have these 5 donuts, right, from closer to further out in the city, and then these are the midpoints of those donuts. So 3/4 of a kilometer, 3 1/4, 7.5, 17, and 37.5 kilometers. And then we calculate the average light in that donut. And so for each city year, we have 5 observations of light intensity. Downtown, a little bit further away, up to 50 kilometers away. And with those 5 points, per city year, we run this very simple linear regression. Light intensity on distance. So you have, oh yeah, it's over here. So we have on X the distance, 0.75. Is that right? Yes. 3.25, 5, sorry, 7.5, and 17.5, and 37. We have the light intensity, and so typically it's brighter over here. So you could have something like this, right? For each city year. And so we just run a bunch of regressions to get at this, what's the best fitting line. And that gives us a sense of how centralized the city is. And I forgot your name. Tyler. A city that's more dense, you see the decay, the slope being very negative. In a city that's spread out, you see the slope being less negative, right? So this would be a more centralized city, right? One where the light decays at a faster rate. This one would be a more decentralized city. And so, does that make sense? So for each city and year, we have we've had the slope, this beta coefficient, and we're going to ask whether that slope is changing with subways? Is it becoming flatter or steeper or nothing? Ariel?
Yeah, I guess, density
In
and
nightlights?
centralization.
Mhm.
I'm thinking of like two, like, big examples of cities, so New York City and Houston.
Mhm.
Houston is like the ultimate decentralized city,
Mhm.
but I would imagine that it has a city core that rapidly decays to suburbs. So it would look very centralized, maybe, whereas New York City, the densest city I've ever lived in, is also the most decentralized city I've ever lived in. It's basically 5 cities crammed together into one, each of them
Mhm.
extremely dense, so it would have very shallow. And I'm just wondering if I'm like, I mean, yeah, like, is that like, does density and centralization, do they typically like move together in any particular way? Because I'm just thinking of these two examples where they actually look opposite.
I mean, the ones we saw kind of made sense. So a city like Houston would look more like this, would look flatter. And a city like New
Really?
York would look like the light just decays much quicker than if it's more centralized. So
Really?
they did make sense, yeah.
Okay.
So they looked, I don't have pictures here, but you know, developed country cities looked a lot more decentralized, and developing country cities looked a lot more like this. Just the lights just, you know, went dark much quicker. Those are other things. Sam?
This is a question from the chat, which I think you're already sort of answering part of, and how well would the radius approach work for coastal cities? There's no light coming from offshore that would create a fire.
Good question. We didn't do anything about coastal cities. And so but we have a lot of years of data. So what we're doing in the exercise is we're looking at changes in that gradient for the same city. So we're not doing cross-city comparisons. So if there's a city that's coastal, then, you know, sure, it's going to be, you know, not the same as though if it didn't have the water, but we're going to be looking at changes within that city. So we think that's not a big concern, but it's worth investigating more. It's funny that you mentioned it, that this person mentions it. When you look at the lights data, it is reflected in the water. Those coastal cities do have light coming out of the water, and it's just reflections that are captured in the satellite. But anyways, no, we don't do much for that, but our analysis is not cross-sectional. It's going to be changes within the same city over time. Tom?
My original question was about gradients for the subway line. Looks like you don't have the resolution to do that.
Actually, you know what, Tom? Let me answer that. We did do it. It's not in the paper. And what you do see, we looked at lights around the subway lines. So we could do these averages, but around the, you know, like these red lines. And you do see that when you build a subway, light gets attracted to those areas, okay? But it dims out in the other non-subway areas. So there's a reorganization. And let me show you that. So let me show you that in the analysis now.
Well, what would be the kilometers of resolution that you would have?
It's about 1K by 1K per pixel. So that's what we get, yeah. Okay, so as I said, so two very simple observations, two very simple operations in QGIS is draw the disks, calculate the average lights in those cities in those years for the full sample, and then run this simple linear regression. And what we're going to be focusing on is the slope and changes in the slope, and also in the intercept. Okay, so we're going to call decentralization if the slope becomes flatter and the central city lights become dimmer, right? Relatively. Okay, so we load the Analyze Me2 lights data set, which is basically created from the Analyze Me. It's just a different version. It's for the lights analysis. So we load that, and now we run this regression. That's the last thing we'll do. But basically very simple. So here we use, you know, ArcGIS and did these calculations, etc. In the end, we're doing just the statistical analysis, right? So how does you know, this is the change in lights in a city. This is for the slope, and this is for the intercept. This is the the beta one, this is the, I think we call it beta zero, the intercept and the, yeah, is that right? Yeah, beta zero is the intercept and beta one is the slope, okay? And so we take the change in the slope as a dependent variable, and the explanatory variable is the change in the subway stations in that 5-year period. And what you see is, this is one of the regressions, but we have, the main thing is that if you build more subways, what you observe is that the slope becomes less negative, so it becomes flatter, and the lights at the origin become lower. So what we're calling decentralization, Ariel, is a city that looks more like this versus one that looks more like this in terms of lights.
Yeah, no, I get that. I'm just wondering what that looks like in terms of like a city.
Well, yeah, what's cool is you can look at these beta ones and beta zeros for each city and see if that
Yeah,
makes
that would
sense.
be really like.
Yeah, I don't have those examples, but yeah, they're in the database. One can look at it. Because we're equating these lights with population. It's not totally right? It could be like more parking lots, etc.
Right, or like a centralized business district with people not there at night
Yeah.
or and like.
Totally.
I don't know.
You know, there are new data sets coming along that actually say they have where are people located, and so those would be even better. I don't know what the source data are. Maybe there are census data. I don't know, but I think there are some new data sets available that are actually, where are people located? And I don't know what the source of data is for that. Maybe buildings from, you predict based on structures.
Like where do they sleep or where are their cell phones?
Again, all these questions are tricky. All right, so I guess, let me see. I think that's what I have. Let me just, yeah, so that's the last bit, the analysis of the night lights. So we do find that, so conclusion one, overall lights, we didn't do this. Overall lights don't change with subways, but the cities become different in the sense that become more decentralized, consistent with the findings of the highways. So just like highways, along the vectors where you reduce transportation costs, you do see activity gearing there, but not overall changes. But that was a surprising result. And as I said, this is reflected in the population and in the lights. And yeah, and so that was our tutorial. Thank you so much. I can stay for questions, but thank you so much for coming.
I'll do a quick announcement. So yeah, thank you so much, Margaret. That was fantastic. Really, really great to see the walkthrough of that. And we'll be posting these videos online as well. So if you know folks who missed this, or if you just want to return to it, you'll be able to. Also, we're asking everyone, please stay for our second workshop this afternoon, the crop type mapping tutorial that'll be run by Shruti Jain and Vivek Sharma, and it'll be that'll start at 12:30. So we'll have a lunch break. People are welcome to grab any of the snacks up here, coffee, or there's you can have the Euclid and there's restaurants around there, and then come back at 12:30 for our second workshop. And as just the final reminder, all the videos for the workshops will be posted on the geo4.dev website. That's where all the tutorials are. I think we'll probably be linking the videos within the tutorials, so you'll be able to both look at the tutorial and go straight to the videos. And yeah, it's just a reminder on our geospatial analysis for development initiatives has other work. We have another set of workshops we did in May. This is one of the main kind of things we're doing for this initiative is building these tutorials and workshops so that folks can access these incredible data sets and approaches that folks like Marco have been working with. And so without any more kind of rambling, we'll let you all go to lunch. And thanks again.
Thank you so much, guys.
Thanks.